Hey guys, after a quick break, we're back. This is just where we left off. Here is our example, and here is the cliffhanger that I left you with. We are now ready to make a decision if we're going to reject or fail to reject this null hypothesis that I made. And to do that, I'm going to partition this distribution where the null is true into a rejection region, and we know what happens in the rejection region. We reject the null. And the acceptance region, you know what happens in the acceptance region? We fail to reject the null. So how do we partition this distribution into an acceptance region and the rejection region? Well, to do this, we decide how often we want to be wrong. To partition it into the rejection region and the acceptance region, we want to decide how often we want to be wrong. So look, right over here, we're going to reject for very small birth weights. Right? My null is right at the cusp of the low birth weight cutoff. So the lower my observed sample average, the more likely I want to reject, I'm going to be to reject my null, right? So my rejection region is going to be out here in this tail. How far to set it? How far to set it? That's what I'm trying to find out. If I set it too far, you can imagine I will almost never reject the null. You know, I will need to have a crazy low birth weight average. If I set it too close to the middle, I will almost always reject the null, right? I deliberately picked this birth weight to be on the cusp. So we really have to work hard to work it out. So to partition the sample distribution into an acceptance region and a rejection region, we need to decide how often we're going to be wrong. All right, when are we going to be wrong? So in the universe, if you were an omnipresent, omni-knowing being, you would know whether the null is true or the null is false. There's no other possibilities. The null is either true or false. We don't know which one it is. But in the universe, either the null is true or the null is false. If the null is true and we reject the null, we're making a mistake. If the null is true and we fail to reject the null, we are okay, right? We are not making a mistake right there. The null is true, we fail to reject the null based on our data. Okay. The other state of the universe. Remember, I said this was going to be philosophical. The only other possible state of the universe is if the null is false. If the null is false and we reject the null, null false, we reject the null, we're not doing anything wrong. Here we are happy as well. Here we're making a mistake. The null is false, but based on our data, we fail to reject. So we encounter the two types of errors in hypothesis testing. This right here is called the type 1 error. Down here, type 2 error. Now, memorization only takes us so far. So let's take a look at these types of errors. Type 1 error is when we reject the null, but it is true. We reject when the null is true. Now, here's how I propose we think about it. This is our false discovery. Recall that the null is set as the hypothesis of no effect. and we are rejecting the null. We're saying there is an effect, right? But we're saying there is an effect when in truth there is not. Like, we're making a false discovery. That's type 1 error. Notice that this is the only kind of error that we can make inside of this distribution, because we assume the null is true to perform our hypothesis test. Type 2 error. We fail to reject when the null is false. So I propose we call that failure to detect. We are on this bottom row. The universe is on this bottom row. There's something happening, right? The hypothesis of no effect is false, but our data doesn't show it. So we are failing to detect an effect, right? Type 1 error, there is nothing happening, but we claim there is. We're making a false discovery. Type 2 error, there's something happening, but our data doesn't detect it. Okay? So inside the sampling distribution, where the null is true, we are just in this top row. We can only make a type 1 error. So we pick our desired type 1 error rate. How often can we accept making a false discovery? And we put that proportion allocate this proportion of possible averages. Why averages? Because that's our variable here, right? It's our sampling distribution to the rejection region. Inside the distribution where the null is true, we can only make a type 1 error. Not saying type 2 error is not important, but it just doesn't happen inside the distribution where the null is true. When we assume the null is true, when we're performing this hypothesis test. So when we're to partition this distribution into a rejection region and an acceptance region, we're going to pick what is our acceptable type 1 error rate. And we're going to allocate this proportion into the rejection region. Okay. See, it's an involved exercise. So any number is possible, guys. Any number is possible. But almost always, and by the way, this is called alpha. The type 1 error rate is called alpha. Probability of making a type 1 error. It's called alpha. By the way, probability of a type 2 error is called beta. The notation is important only because you're going to see it in the literature. Almost always, we set alpha as either 0.1, 0.05, 0.01, and I hate to do this, but if you're trying to get published, most often people will pick 5%. 5% as the most common type 1 error rate. But there's no good reason for this other than that's how we do it. That is the number we have selected. That is the number that Dr. Fisher said about 100 years ago was good enough for him. About 100 years ago, he said, I think 1 in 20 times would be an acceptable, false discovery rate, and that is how the 5% mark stuck. So let's roll with the 5% mark, though others are possible, right? So I'm going to put 5% of the possibilities into that rejection region. Okay, so I can use what I know about z-scores to find out a few things. Well, what is this cutoff here? What is the cutoff between, this is the rejection region cutoff on the z-score scale. Remember, z-scores don't care what this variable is. It could be, blood pressure. It could be height and weight. It could be average birth weight. Right over here under the mean, it is 0. We are definitely in the negative numbers, right? This right here is our observed X bar z-score. Okay, so if we can only figure out what our observed z-score is and what this cutoff is, we can decide if we are in the rejection region. And if we're in the rejection region, then we will reject the null. So 5% of the possibilities go there. We can use the app, right? We're going to go value from an area, right? It's a z-score that leaves 5% below. Why 5%? We decided 5% is an appropriate type 1 error rate, appropriate false discovery rate. Why false discovery rate? We're working inside a distribution where we assume the null is true. We decided 5% is an appropriate false discovery rate, and value from an area, z-score that leaves 5% below itself, is negative 1.645. I said we took a sample of size 16, and I said we assume that our population sigma is known. So I can compute the z-score for my observed sample mean. Okay, so compared to the other z-score that we know, right? We did x minus mu over sigma. But my observation is now not x, but x bar. Right? That's what I just observed as my sample average. My mu is 2.5. Why 2.5? The first thing I do is I assume the null is true. And I work inside the sampling distribution where the null is true. That sigma right there is sigma over root n, right? This is the standard deviation of x bar. Sigma is known, 0.635. Sample size is known, 16. That's why I picked 16. And what I observed out of my 16 observations was a birth weight of 2.3. So when I compute the z-score, I get a negative 1.258. Negative 1.258. So it is now very clear that we are not in the rejection region. We are in the acceptance region, right? We picked the rejection region because we wanted to have a 5% false discovery rate. On the z-score scale, that number is negative 1.645 because that is the number that leaves 5% below itself. With our observed sample mean, our z-score is negative 1.258. So we are not in the rejection region. All right, guys, I know it's exciting to watch me erase. Negative 1.258 is not in the rejection region. So we're going to fail to reject the null. Now, these things have certain names. The z-score that is associated with our observed average is called the test statistic. This rejection region cutoff is called the critical value. And so we ended up comparing the test statistic to the critical value. The critical value is based on your alpha level, right? This 5% false discovery rate is also called our alpha level. And 1 minus the alpha level is the confidence level. See, these are just all definitions. They're important definitions. But they don't do anything, for the mechanics of this exercise. One more time, the test statistic is the z-score for our observed sample average. The rejection region cutoff is called the critical value. And this 5% right here is the alpha level. 1 minus the alpha level is the confidence level. So 95, if the alpha level is 5%, the confidence level is 95%. Okay. But I promised you a p-value, didn't I? I promised you guys a p-value. So, very important. The p-value is a very complicated and convoluted definition. It is the probability of observing a more extreme test statistic than the one computed using our data. It's the probability. Okay, so the p-value is a probability always between 0 and 1. It's the probability of observing a more extreme test statistic. So we observed a test statistic of negative 1.258, again, associated with our observed average. More extreme is into this tail, right? more extreme following the stated alternative. Right, my alternative is only below. I'm only going to reject my null for low birth weights. So more extreme is into this tail. So for us, it's the probability of z being less than negative 2.58. And negative 1.258 is then again the z-score associated with my observed sample average. So we can use the app to compute this. And this is 0.104. That is the p-value associated with these set of hypotheses. If I have a sample size of 16, sigma is known to be 0.635, and I observe 2.3 as my sample average. Now, down here, I've already came to a conclusion that I'm going to fail to reject the null, because neither my observed average nor the test statistic fell into the rejection region, not in the rejection region. At the same time, you can also use the p-value. P-value is greater than alpha, right? P-value is here, right? P-value is from my observed test statistic more extreme according to my alternative hypothesis. It is bigger than my alpha level, my 5% alpha level that I selected based on my false discovery rate. So p-value is greater than alpha, means I fail to reject the null. Notice that these happen at exactly the same time. When we're outside the rejection region, our p-value is going to be greater than alpha. If I'm inside the rejection region, my p-value is less than alpha. Both of these conclusions that I failed to reject the null, their interpretation is that although my observed average is lower than the low birth weight cutoff, it is not statistically significantly lower at this alpha level. So let's write that down somewhere. Fail to reject the null means my observed sample is not statistically significantly lower or rather even better. The population that produced my sample, the population that produced my sample is not statistically significantly lower than the low birth weight cutoff. So my newborns are not below the population from which my newborns came from, are not below 2.5 kilograms. Even though my observed sample average is below 2.5, it is not sufficiently below to call that difference statistically significant. Let's do one quick thing before we wrap up. This was based on a sample size of 16. What if we keep literally everything else the same, but now take a sample size of 100? So I'm going to just redraw the picture, make the conclusion, and we're going to call it quits. What if sample size was 100, we still had sigma being 0.635, X bar observed was still 2.3. All right. My null is again set at that low birth weight cutoff. My alternative is below. I only reject for newborns that have a low birth weight. Here is my X bar birth weight scale. I know that right underneath it are z-scores, and I can transform any of my observed averages into a z-score. I know that the distribution of my sample averages is a normal distribution. With some mean and some standard deviation. And I know that we assume the null is true we suppose the null is true, and the standard deviation of my sample averages is sigma over root n. Sigma is 0.635. And my n is 100 in this scenario. Before it was 16, we failed to reject. Here it's 100. But notice I did not change my observed average. Okay, let's suppose that the null is true. When we say we suppose the null is true, we basically put the null value right here in the middle. Okay, and we know this is, of course, associated with a z-score of 0. I just observed 2.3. My average birth weight is 2.3 kilograms. Now, with a sample size of 100, remember this is called the test statistic. My test statistic will now be different, the sample size of 100. Because X bar minus mu 0, that's my null value, divided by sigma over root n. This is the same as the previous example. This is the same as the previous example. This is the same as the previous example. Only the sample size is different. Now we get negative 0.2 divided by 0.635 over 10. And this is negative 3.15. This is my test statistic. In my rejection region, I'm going to put 5%, right? That is my acceptable false discovery rate. Well, this is where I guess the drawings break down a little bit. This cutoff right here is my critical value, right? 5% over here. And this is my rejection region. That critical value doesn't change. It's negative 1.645. It's the z-square that leaves 5% below itself. But my test statistic is now negative 0.315. Negative 3.15. With n equals 100, we are well into the rejection region. Test statistic is less than the critical value. Reject the null. Right? This test statistic is well below the critical value, so we're going to reject the null. We're now well into the rejection region. And the p-value, I'm going to find the p-value up here. P-value, probability of a more extreme test statistic following my alternative hypothesis than the one computed using my data. And this is 0, it's 308. Minuscule. Also, p-value is less than alpha, right? My p-value was 0.8. My alpha was 0.05. Reject the null. So for the same average, when I just change my sample size, I now can say that my newborns with this average came from a population that is significantly below the low birth weight cutoff. With 16, although my average was below, there was too much uncertainty. I couldn't say that. With 100, I now reject the null. I say that my population of newborns is below the low birth weight cutoff. Thank you guys for sticking with me. This is a tough lift. I'm looking forward to seeing you soon. Have a great night.